Okay, let's see. These numbers. All right. Good morning. Conditions. Today, we're going to continue on talking about galvanic cells, the super exciting batteries, and all that good stuff. Oh, goodness. Hold on. Okay, but today we're going to finally talk about them under non-standard conditions. So we're not going to have our 1 molar anymore. Typically, we're still going to be at 25 degrees Celsius, but technically we don't have to be. Yes, good morning. Okay, so last time we saw that we could use the Faraday constant as well as moles of electrons to go from our cell potential to a delta G value for the reaction, which we also know was how we can relate this to the equilibrium constant, right? We also now remember delta G we could relate delta G at non-standard conditions to the standard delta G plus the term containing the reaction quotient at our given particular time, whatever that happens to be. And then if we have that the standard delta G would be related to the standard cell potential, we can go ahead and expand that to getting rid of the standard conditions for the other delta G. And so we can plug all this fun stuff in. Oops. If we just substitute in those delta G values, wow, she just zoomed up on the couch. So we've got all this fun stuff now. So if we wanted, we could rearrange some stuff here. For example, we could have actually that's going to have to be a minus sign. We can solve this thing for E. And so, therefore, no, positive E. Plus, or rather minus, we can say. We can relate all this fun, good stuff to our reaction quotient at a given time. So we can now throw our standard cell potential in terms of the volts that would be able to generate, and then we can adjust for non-standard conditions. So that would be including, for example, the temperature and the reaction quotient. R, N, and F well, n is not a constant, but r and f are constants, right? For whatever reason, people like to adjust this equation further. I think it's fine as is, but why not? I can show you what some people will do with this. They can kind of lump all those constants together. I have to remember what this number is going to be in minus 2.303 log Q. Yes. This is going to be at 25 degrees Celsius. Changing the base for the... oh, I'm sorry, I forgot the RT, didn't I? And so just changing it from natural log base or base E logarithm to base 10 logarithm. I'm not really sure what the purpose of that is, because I mean our calculators do either one just the same way, but perhaps it's easier to use base 10 logs. Whatever works. And then if we want to kind of adjust this for room temperature, for 25 degrees Celsius, we can throw in all those constants, the RT and F, at 25 degrees Celsius to get, what's the number here going to be? 0.0592 log Q over N. And that's kind of the most common, I would say, form of this equation. So this is again at 25 degrees Celsius or 270 or 98.15 Kelvin. So this is what's commonly used here. This is, by the way, called the Nernst equation. Figure we'll give a name to it. Why not? It's again how we're going to relate standard conditions to non-standard conditions. Typically, though, again, because most cells are run at room temperature, we're looking more for the reaction quotient here. Instead of having this at standard conditions, which would be 1 molar, we can see what's going to happen at different molarities. So we have some here. Let's do an example. Okay, so what was the example here? Okay, so if we take a look at that one we did yesterday where we had the zinc and the copper. If I remember correctly, the copper was being reduced. Is that right? Yeah. It was. It was. Let me know if I'm lying to you. This was the equation we did yesterday. If we look at Q for this reaction, remember Q only includes aqueous products and reactants. Zinc to the Z plus power. Zinc 2 plus over copper 2 plus. So if we have and 5 molar copper, we can figure out what the concentrate or our cell potential is going to be at these conditions. So standard conditions again would be 1 molar of each, where Q would just be 1, right? If Q is 1, ln of 1 is 0, cancels out all that other term. E is equal to E cell or E standard. But if we do this, we're going to have our cell potential here minus, what was the number, 0.0592? That's right. Times the log of Q. Q we saw was equal to zinc over copper. Mm-hmm. Of course, for this reaction, n is going to be 2, right? If we plug all this fun stuff in, what was the value we calculated yesterday for this reaction? Let's go check real quick, unless someone has it off the top of their heads. Maybe it was up here. Wait, yes it was. Okay, I saw it. So 1.1. Okay, cool. Oh, and of course Kevin had the answer and I didn't even look up. Okay. Wow. 1.1 volts minus 0.0592. Units for that is volts as well. We have 2 electrons happening in this reaction. We have the log of 0.05 over 5. So that should be negative 2, right? So we're going to get 1.1 plus, actually that'll just cancel out, right? So plus 0.0592. Am I going crazy? No, I think that's right. Log of, yeah. So doing this stuff, yes, indeed, we get positive 1.16 volts. So we see we have increased our cell potential. Hold on, Oz is gonna cry if I don't put him on the couch. Oz, there's stairs right there. You can go up yourself. Okay, there we go. And so notice, we in this case we have a lot of our reactants, a little bit. So we know that Q is going to be definitely, I can do this, less than K. Thinking about it in my head, too many reactants, K becomes smaller. Yeah. So we're going to have Q is less than K here. So as a result, we're going to end up with extra potential that we come out of this. So basically, we just have more reactants, more electricity, more potential, rather. So we ended up with a little bit higher than normal here. So lucky us, hooray. All right, any questions on that one? We can do a couple of examples from our book. We'll go through them. All right, let's see. So we've got, oh, how lovely, a dichromate reaction and iodide. Okay. Let's balance this reaction. Let's practice this. Let's do it in acidic solution. We're going to get chromium 3 plus. Plus I2. Let's go ahead and balance this thing in acidic solution. And then let's calculate it when... Let's go ahead and figure this out. Let's calculate... Concentration of this is 2 molar. H plus is 1 molar. Iodine is 1 molar. Iodide, rather, is 1 molar. And then, what do we have? The chromium is 1 times 10 to the negative 5. Okay. Okay. Let's do this. So, in the book, they've given the actual equation, but let's practice our balancing skills. Let's do this in acidic solution. So we have our half reactions here. We have dichromate turning into chromium 3+. If we want to balance this, first thing first, we want to balance our chromiums. Then we want to worry about oxygens. So we're going to add 7 waters. Now we have to worry about hydrogens. So we're going to add 14 hydrogens. And look at the charge. We have 12 plus on the left, 6 plus on the right. So we need 6 electrons to balance this out. All right, so that's that first half reaction. Let's see what we've got here for the second one. We've got 6I minus, you say? Makes sense. Actually, let me give myself a little bit more room. All right, so indeed, first we're going to have 2 iodides, and we're going to need to put out 2 electrons. But indeed, we are going to need to multiply this later on. So we're going to want to multiply this by 3 to get 6 iodides. Turns into 3 iodines plus 6 electrons. Now we can go ahead and clump all this together. So if we add all this stuff, we get 6I minus plus 14H plus the dichromate. Turns into 2 chromium 3s plus 7 waters and 3 iodines. Okay. Okay. So we have done our balancing. Definitely going to need a lot of hydrogens here to make things work. All right. Any questions on the balancing, by the way? Hopefully that should be getting easier as we do more and more of it. We know that the E for this reaction, 0.0592 over N times the log of Q. And in this reaction is going to be 6. We know that because we just balanced the half reactions. We saw that 6 electrons are being dealt with here. We're going to have to go ahead and figure out our potential here. So we have dichromate is going to be reduced to chromium 3. And then we're having iodide be oxidized to iodine. So remember, that's always, it's going to be the cathode, which is going to be your reduction one, minus your oxidation one. The reduction is going to be the dichromate, and the oxidation is the iodide. They're technically, we always write them as reduction potentials, right? So we should write that as this. Let's go ahead and pop open Wikipedia to find our list of fun. Where are we? Okay, standard electrode potentials. Let's find iodine on this. Oh, iodine was the pain, right? Because everything is an I in this. Okay, I2, yeah. So it's plus 54. 0.54 rather. Iodine plus 2 electrons, yes. And then we have dichromate here. Chromium, that looks to be 1.33 volts. All right, according to our list. Yes, okay. And so doing this math, we get 0.79, 69, 79. Oh, thank goodness I did it. Okay, cool. So we do get that this is a spontaneous reaction. That's awesome. It's always a good thing to see. If we want to find out Q for this reaction, it's going to be a bit more complex, right? This has got more going on than just the plain. Oh, I've gotten past our reaction. Here it is. We have no, none of that. We have kind of 4 aqueous components in this reaction. So we've got the chromiums on top. We have the H plus on the bottom. We have the chromium or dichromate. And then the, what was the other one? The iodine to the 6th power. Thankfully for us, H and I are just 1, so we don't have to actually worry about these crazy exponents. So because they're 1, let's just kind of get rid of them if that's okay with everybody. They're just 1. You know, let me not do that because I don't want people to think like we're just canceling them out for some reason. But we can do this. So E equals 0.79 minus 0.0592 over 6 times the log of, what was the, it was 10 to the minus 5, is that right? Yeah. 10 to the minus 10 over 2. If we plug in all of our stuff appropriately. Right, because 10 to the minus 5 squared would be 10 to the minus 10. And then the other 2 were just 1. So we can finally do this. And thank goodness the book has the answer because I don't want to actually have to like do this math. Doing all this fun stuff, we get 0.89 volts. Hooray! So again, we have more reactants than products, so we are expecting a larger potential than we would otherwise. So electrochemistry is fun, right? Easy. Any questions on that one? If not, we can do another one. Oh, that's a fun one. All right, no questions. Let's do another example. This one in the book is example 20.12. In the book, so we have a zinc hydrogen cell. We have a zinc. I'm going to not give us all the answers. It's giving us the cell potential, but I don't want to do that right away. Temperature is that. What's the pH of the cathode? That is what the question is asking us. And let's just throw one more sig fig in there. So, pH of the cathode. Cathode, remember, is the reduction side of things. Remember, red cat is our anagram, or not anagram, mnemonic. So we're going to have reduction of H+. So that means at the cathode we have the reduction of this. And then the other side, we have the oxidation of zinc. That's what's happening here. So if we put these together, our overall reaction we're going to have overall this. So I think the last thing, by the way, I forgot to tell us, I forgot to give us E. E was given in the equation, or given in the problem as 0.45 volts. Now we can find out what the pH is going to be of the cathode. So let's plop out our Nernst equation as always. All right, so we know we have 0.40. Actually, let's calculate E cell. We have the reduction minus the oxidation. So we know that this is 0 volts. That's hydrogen. Remember, standard hydrogen electrode should be 0. Let's find zinc on our list here. Zinc, zinc, zinc. Here it is. It's negative 0.76. All right, so we end up getting plus 0.76 as our E at standard conditions. So we have 0.45 volts, 0.76 volts, minus 0.0592. We have 2 electrons in this process. Log Q. For this reaction, Q is equal to, we have H2 zinc on top and H plus squared on the bottom. We do not know H plus, right? Otherwise we could just calculate the pH directly. So we just have kind of 1 over x squared for our Q. So let's see here. What shall we do? Oh goodness, we have all this stuff to deal with. Okay, so if we're to solve this equation, log Q will equal to two over 0.0592 negative that times 0.45 minus 0.76. All right, which will equal, okay, negative 2 divided by 0.0592 times 0.45 minus 0.76. Log Q is going to be 10 point, is this positive or, no, it is positive. Okay, 10.47. So Q equals, I think I've done the math wrong here. Let me see. 2 divided by that times that. Okay, well, whatever we get. So Q is going to equal to 10 to the 10.47, which is going to be 1 over x squared. Oh, thank goodness, it's not 10. Did I? It says 1.47. Here, maybe the. Let's see if we have it here in the problem, because I hate calculating with this. No, I think it is something really big like this. So if we solve for x squared, we are going to get x is equal to 3 point. Oh, that's sorry. X squared will equal to 3 times 10 to the negative 11, or x will equal to 6 times 10 to the negative 6. Double check that you had the 0 properly before the 5. That would be my guess in the calculation, because this answer seems to make sense. So, and according to Google, I have put in everything correctly. So at least the way I see it here. So double check yours. If therefore the H plus concentration will be 6 times 10 to the negative 6. And the pH will be, what's it going to be? Negative log of that, which will be 5.2. Double check, Kevin. Have you gotten 10.47 this time? I hope you did. So, lots of fun stuff we can do with these. All right, all right, here we go. Google time. Something's gone wrong here. So I do get this when I plug it all in. Just make sure that I think this 0 might have gone missing in your calculation. What the heck kind of these are the weirdest things that come up with this. But yeah, I think you might have forgotten this 0 here, because that'll be the difference, I think, with this. So double check that. It looks to me that I've entered everything correctly here, so double check it. Okay, cool. So anyways, once you do that, you end up solving for x. Again, you can just use your solve for x calculator, or you can just do the square root of this thing and invert it. You'll get 6 times 10 to the negative 6. Throw it into your pH. Since this is just going to be H plus as is, we can just calculate the pH directly. And so there we have it. Fun stuff. Fun stuff. Alrighty, any questions on that one? That was a bit harder solving for Q this time instead of E. Any questions on that one? All right, well, let's move on to another one. So with this idea of non-standard conditions, we can also have just concentration gradients that'll produce electricity for us, as they will try and equalize themselves. We know concentration gradients always try to equilibrate, right? Whether you have that through osmosis or diffusion. It's pretty interesting. You can have that with electronic cells as well. So you can have the same metal electrode and just have a more concentrated solution and a less concentrated solution. And you'll see that you will be able to generate potential this way. The book has one starting with a nickel example. We can do that. So we can see what's going to happen with a concentration cell like this by looking at the Nernst equation as always. So with this, indeed. So with this, hopefully we can see that standard conditions we would get no potential with this. Obviously because we have the same reaction oxidizing and reducing itself. So we're not going to have any voltage from standard conditions, but these are not standard conditions, are they? So we can actually get a voltage out of this. So we're going to see that. Why do I keep writing Z up there? We're going to essentially have some nickel that's going to be plating itself, and some nickel that is going to be becoming oxidized, right? So some nickel will reduce itself. We're going to see that as we do this, the electrons are going to move from the less concentrated side to the more concentrated side. We're going to see that we have... Hold on, let me write this out. From less concentrated to more concentrated. So as Kevin has said, yes, it's going to act as the anode. So the electrons are going to move from the less concentrated side to the more concentrated side to get rid of some of those extra zinc ions, or I'm sorry, nickel ions in the more concentrated cell. So what's going to happen here, as a result, we know that we have our reaction here is going to we can calculate Q for it. We're going to have nickel and nickel, right? Exciting stuff. But we're going to see that the actual potential for this thing, remember, is 0 for standard conditions. But we're going to have kind of the concentrated one and the dilute one here. We're going to have our anode on the top, our cathode on the bottom, as always. This is going to be the less concentrated on the top. What was the other one? 1. For the cathode here. And so if we do this, the log of Q will just be -3. So if we do this, we have 0 volts minus 0.0592 over 2 electrons that are being transferred, right? Because nickel 2 plus. And then we have -3 for our log Q. doing this fun stuff. Thank you, Kevin. We do get some voltage out of this. So electrons are going to move to kind of stabilize the reaction as it goes. We're going to see eventually they will equilibrate. This process kind of will, since it is Q, we can imagine kinetics are happening. We're going to go really fast at the start. We're going to slow down towards the end. Probably first order kinetics with this one. And so we're going to see this is kind of the initial potential, and the potential will decrease over time. So fun stuff. So just kind of cool stuff you can do with this electrochemistry stuff. We can talk about batteries too. I think there are some examples of batteries here. Yeah. These reactions that are just crazy. So let's talk about batteries. One common one is the lead acid battery, which is what's in your car. Crazy equation here. We have lead 4 oxide plus hydrogen sulfate plus how many electrons? 3 hydrogens plus 2 electrons, turning into lead sulfate and water. I can make this nice, actually. I can put this all on one line. Yeah, we fit it. Cool. And then you also just have, at the anode, you have the other side of the reaction. You've got lead and the hydrogen sulfate, again, turning into PbSO4 plus 1 hydrogen and 2 electrons. Putting these together, we can see we are oxidizing here, we're reducing here. We're going from lead 4 to lead 2, that's reducing, and we're going from lead 0 to lead 2, that is going to be oxidizing. Putting these guys together, turns into 2 lead sulfate and a water. So this one is nice in that we have lead 4 and lead 0 coming together to both form lead 2, which is going to be nice because when we reverse this reaction, we are going to end up getting both out again. So we can kind of recharge this battery in this manner. The potential for this, if you were to calculate it, is 2.05 volts, which may not seem like a lot, but that's the standard potential, right? So we're going to see that we can kind of mess with this by throwing in more concentration and all that sort of fun stuff here as we go through it. So this is just commonly what's in your car. So you'll use this battery to start your car. As you are driving, your alternator will generate electricity that will reverse the reaction. So this reaction normally will put out 2.05 volts. If you put in 2.05 volts, you can get the reverse reaction to happen. Take your lead sulfates back into the lead 4 oxide and the lead by itself. These also will plate the lead sulfate on kind of the electrodes. So it's already going to be in a very nice position for it to kind of go back into solution and go back to be ready to be used again next time. So these are kind of self-recharging as you drive, which is nice. So we don't have to replace them very often. So pretty cool things there. We have also less rechargeable ones. So just note, because this is lead 2, we can then disproportionate this back into lead 0 and lead 4, that lends this to be rechargeable. As a result. So the lead 2 of the electrons can go to one lead, and then the other lead will be left with 4 plus, and so you can kind of regenerate your stuff as you go through. So very nice, very nice. All right. Alkaline batteries, like you'll see, are your AA and your AAA and all those things in your remotes and all that sort of fun stuff. That kind of like Duracell, you think about these are the Energizer batteries. How these work, your cathode is going to be manganese 4. We have some water and electrons. We're going to reduce that to manganese with a hydroxide as well. So we're going to have manganese 3 and 2 hydroxides. Oops. Note that these are alkaline, so they're basic batteries. So we are balancing in basic solution, essentially. We have hydroxides instead of acid, as we had in the other one. The anode for these batteries is usually, it's zinc. Okay. And you're going to form zinc hydroxide plus our 2 electrons. We're going to see, we can calculate E for these just like before, but where is it? This is about 1.3 volts, if I remember correctly when I calculated it, something like that. So we can see that we can get voltages to happen in either acid or base conditions with various different compounds here. And by varying the concentration and kind of the number of cells that you have in a battery, you can really ramp these up to high voltages if you really want to. So obviously 2 volts is not going to be enough to start a car, right? Like we know that 2 volts is, we have 12 volt, little batteries here, but your lead battery in your car is pretty big, right? So you actually have quite a few cells in there. So you just have kind of alternating anodes and cathodes within your batteries that are kind of linked together in series that you can kind of combine the voltages of as you do it. And so with these kind of typical cells within these batteries, again, you can kind of combine them in different ways. This particular alkaline battery is not rechargeable. We're going to see that we're going to end up not having the kind of same product to work with at the end that we started with. So we can't just disproportionate and go back to where we were. So this particular one will be not rechargeable, sadly. Oh well. Let's do something fun. Let's say we want to take a look at, there's that story, you put batteries in the fridge, they'll last longer or whatever. Let's see what happens with that. Let's compare the voltage of a battery at room temperature versus non-room temperature. Let's do this just for fun. So, if we go back a little bit, we remember that we had RT ln Q over our NF here. So remember at 25 degrees Celsius, we can just put in the 0.0592 and we'll be okay. But in this case, we don't have that. But let's say the batteries are going to be the same. So we also know that R and an F would be the same because it's the same battery. What's going to happen with the temperature effects of this? Well, it depends on Q, right? Because if Q is going to be less than K, which it should be, we typically want extra reactants in this case, then we're going to see that the temperature will, what's going to happen with it? If Q is less than K, we're just going to assume that ln Q is going to be negative, we'll say. Less than 1. Let's just say less than 1, actually. And that means that the temperature, increase temperature will be increase our potential. But if Q is greater than 1, and I don't know how to write that, an increase in temperature will decrease E. So, indeed. So typically, again, that means that lowering temperature will decrease your potential. Yeah, which most batteries should be less than 1, right? So we typically want a high concentration of reactants and low concentration of products in our cells. So with this, so your lower temperature will decrease your potential. So that means you're going to get less electricity out of it if it stays at 4 degrees Celsius from your fridge. So is that going to prolong the lifespan of your battery? Probably not, because you're going to have less. If it stays at 4 degrees Celsius, you're going to have less potential to work with, so it's going to last shorter. Before it goes to 0, right? So as a result, putting your batteries in the fridge will actually decrease their lifespan. However, it doesn't really matter. Throwing in the fridge will kind of prevent accidental discharge, but that doesn't normally happen with batteries anyway. So there's not really a point there. But as soon as you take it out of the fridge and put it in your device, it's going to come up to room temperature anyway. So it's probably not going to really have a huge impact. But if you were to pretend that everything were in a fridge, indeed you will see that a lower temperature for most batteries, you'll end up with a shorter life for your battery. It'll have less potential and be able to do less work overall, so it'll last less long for the same amount of work. So, hooray. Now we know. Don't put your batteries in the fridge. No point to doing that. I mean, again, it might preserve them longer. They already last, 15 years or something before they say get new alkaline batteries, so I don't know that would really make a huge difference. Putting it in the fridge, you might get, an extra year out of it, but who wants 16-year-old batteries from the fridge? Doesn't make too much sense. So, there we have it. Alrighty, so we have just a little bit left. We'll talk about lithium batteries next time. We'll talk about electrolysis as well. And then we'll be done with the electrochem stuff. So I'll put up your homework today. It's not going to be due this weekend because we still have a little bit to do. But yeah, we'll have fun with this stuff. So, excuse me. So, we'll do it. All right. So with that, have a good weekend. Honors people, I'll see you tomorrow. I'll give you some fun problems. Electrochem can get really exciting. You'll love it. So, cool. See you next week, everyone. Enjoy your weekends. Remember, no exam on Monday. Definitely not. We pushed it. So, next week. Alrighty. See ya.